want to share some thoughts about the design of Sharp turbines. This doesn't come from any peer-reviewed journal or anything like that. These are just my own thoughts. You can take them with a grain of salt. But anyhow, this is just an explanation of why I designed the small turbine the way I did. So to start out with, if we have there's a topic called induction. Not all the air approaching a turbine goes through. It develops kind of a pressure in front of it, and some of the air gets diverted one way or the other. And so we have, if we just show a fixed wing here and the wind is coming straight down in this direction, we can express some of the wind that it feels as the tip speed ratio times the wind speed. So this thing is spinning, and because it's spinning, it feels a wind going perpendicular to the arm. But then it also has the wind as it's coming in, but not all of it comes in. There's some induction factor, so it's some fraction of the full wind. And the apparent wind that this wing sees is a combination of these two wind vectors here, so it would be this. So we have this angle of attack, alpha, and this A here I'm just calling an induction factor. So this has a factor of U in it, this has a factor of U in it, so really this angle is defined by this number A, the induction factor, and the tip speed ratio. You can take the inverse tangent if you want to get this angle. So what really matters is this ratio of the induction factor to the tip speed ratio. If this is a big number, that means this is fairly large compared to that. You have a high angle of attack, and so if it hits this wing at a high angle of attack, you're going to get stall, and this wing is going to lose its lift and its efficiency because it has a lot of drag. Inversely, if this induction factor is or if this ratio is small, you'd have a small angle of attack, and then the air can stay attached to the wing. So if we want to avoid stall, we can have either a high tip speed ratio, like you see in some big turbines, they'll have tip speed ratios of 4 or higher. That way the wind stays attached to the air stays attached to the wing. Or you could have a low induction factor, A, and one way you can do that is you could have a high solidity on your turbine. So if you have large wings or a lot of wings, then it creates a pressure in front of it, and the wind gets diverted. And so you don't get as much air going through, but it stays attached because this angle of attack is small. And then there's the other solution. You could let the wing pivot, and that's what the Sharp VAWT does. So it allows it to pivot and develop a smaller angle of attack so it doesn't stall. Okay, so that's the Sharp VAWT. It's going to have a pivoting wing. And so here's just a diagram. Here's the pivot for the wing, and we put a counterbalance on here so that the mass is like right at the tip of the wing. Doesn't have to be right there, but typically you do. And here's the wing drawn here. The length of this pivot arm can vary too. I usually use a quarter chord. So whatever this chord is, I take a quarter of that, and that's my pivot length. That's just what I've been using. So here's the wing on the pivot, and what happens in the Sharp VAWT is you have this angle of attack. The wind is coming at an angle, so you get drag, and that tends to want to rock this backwards. You have lift that also wants to rock it backwards so that it weather vanes, so that the wing will align itself with the incoming wind. However, there's a pendulum here with the mass pulling outward on it, so it tends to pull it back a certain amount, and that develops an angle of attack, which creates lift and drives the turbine forward. However, this angle of attack is going to depend on the balance between this inertial force here, the pendulum wanting to right itself, and the aerodynamic forces, the drag and the lift, that tend to want to pull it back. And looking at the equations and so on, I noticed there's a pattern. This ratio comes up here, and I'm just calling it a Bosch number, BO, just for grins. And it's the ratio of the inertial forces to the aerodynamic forces. So the inertial force is related to the mass, and it's also got this factor R in here because as you go with smaller and smaller turbines, that's got a higher and higher amount of acceleration because you're going in such a small radius, and so that actually affects the inertial forces too. And then I've got the fluid density, because the forces will vary with the density, and then you've got the area of the wing. I'm just calling it S here so it doesn't get confused with the area of the turbine. So you've got, usually with air, you've got the wing mass up on top, the fluid density, which is around 1.2 kilograms per meter cubed for air. This R is the radius of the turbine, and this S is the wing area, which is the chord times however high this wing is. So this turns out to be a dimensionless number, and in general, the mass will increase with the cube of the length. So if you double the size of something, you double the width and the height and the depth. And so the mass tends to go up with the cube of the length. And the area of the wing only goes up with the square of the length. So when you double the size of it, you only end up doubling the chord times the double height. So that's the length squared. But then this R also scales with the length, because if you double it, then the radius of the turbine doubles. And that's nice because what ends up happening is you have length times to the cubed in the numerator and length cubed in the denominator. And so in theory, it should be possible to maintain this balance between inertial forces and aerodynamic forces while you're scaling the turbine up and down. Okay, another issue that comes up with Sharp turbines is how fast can this wing react. And this isn't a real in-depth analysis of that. But the wing is basically on a pendulum. And what I do, well, if you have a pendulum on Earth with 1 g of acceleration downward, there's a fairly defined formula for the period of the pendulum, and it's 2 pi L, the length of the pendulum, over g. And in this case, if you want metric, g is 9.81 meters per second squared. But anyhow, the wing is not just, this is for a point mass on a string. The wing is not a point mass, it's got some inertia to it. And so if you separate the wing and the counterbalance, you can increase the inertia, and that's going to affect things. But for the most part, it's defined by geometry, and if you keep the geometry the same as you're scaling, it should change with the square root of your length, or whatever you're scaling it. Okay, we want to make sure that this pendulum can react fast enough, so we'd like it to be able to swing one way or the other within a rotation of the turbine, or preferably even faster than that. And so what speed we want to compare it to is when the turbine develops an acceleration that's equal to g. I mean, we test the period of a pendulum in a 1g field. We want to increase the speed of the turbine, or just run the turbine so that the wing is feeling a 1g acceleration, and that you can just write as radius of the turbine times omega squared. And that's your acceleration. We can set it equal to g. Solve for the speed of the turbine, square root of g over r, and that's in radians per second. We want to convert that to a period, so we invert it. We'll go 1 over wg, multiply it by 2 pi, and then you've got square root of r over g, and that's seconds per revolution. So what we'd like is, as we scale the turbine up and down, we'd like that the period of the pendulum varies the same as the period of the turbine, so it doesn't become an issue. And sure enough, we have the square root of L here and the square root of R here, so you double this, it goes up by the square root of 2, you double this, square root of 2. So basically you should be able to scale up and down and not have to worry about the period of rocking of your pendulum. If it worked at one speed, it should work at another speed. Okay, so the scaling isn't a big issue. So what's the problem? Well, as you get to smaller turbines, the acceleration gets really large. You're going in a small circle, and if you want to keep that tip at a certain tip speed, you get some very high RPMs, and then the acceleration goes up with the RPM squared. And so you get some high accelerations with small turbines. And so your wings need to be strong compared with their mass. They have to be pretty rigid so that they can handle the RPM. And also, what I've been finding is that this dimensionless number that should be the same as you go up and down, it tends to get higher with the small turbines. Maybe the mass per unit area of wing stays the same, but then you've got this R term in the denominator, and so that because the acceleration gets large, the dynamic forces get higher relative to the aerodynamic forces, or the inertial forces get high relative to aerodynamic forces. And so it acts like the wing is heavier than it is, and so you get a higher angle of attack. The wing is not moving as much with the air, and it's acting more and more like a fixed wing, so you get higher angle of attacks. So anyhow, how are we going to combat these problems? Well, one way to do it is to reduce the tip speed ratio as you get to a smaller turbine. So instead of having, like the big turbines do, a four times the speed of the wind, maybe your tip speed ratio goes down to 1 for a very small one. So you can cut down on the tip speed ratio, and that cuts down on the acceleration. Another thing you can do is, if you've got these high angle of attacks, you can increase the solidity with smaller turbines to reduce the amount of air being induced and cut down on the angle of attack, and so then the air can stay attached. And one thing we want to do is we want to increase the solidity, but we don't want this chord to get scaled, go larger because of this increased solidity. So one thing you can do is you can change the number of blades to keep the chord scaled with the turbine diameter. Okay, so if you have the turbine diameter, you can have the chord, but then you just put more blades on to keep your solidity up. So anyhow, I made a table. This is just some thoughts. It's not anything very scientific, but it's hopefully a guideline or just looking at some design ideas. What I did was I put the turbines in various size categories, like 0.25, 0.5. I just doubled them, 1, 2, 4, so doubling the size every time. And the big ones would probably have a tip speed ratio around 4, little ones around 1. Ones that I'm used to working with probably around 2, so you probably want to run at those speeds. And what I did was I just multiplied this by square root of 2, square root of 2, square root. So I just used that multiplier going all the way up. And looking at solidity, I've been finding that 0.3 was pretty good for a turbine. And if it's one of these big ones, they probably run at a lower solidity, like 0.15. And if it's approaching a fixed wing turbine, they usually run around 0.6 solidity. And so I just did the same sort of thing, this times square root of 2 times square root of 2, so on. I just filled in these numbers to sort of blended. So we'd like the chord to stay kind of in those same kind of ratios. And so I looked at different numbers of blades. So we got like 3 blades, 4 blades, 5 blades, 6 blades, 7 blades. And if you figure the chord being this solidity times the diameter divided by number of blades, if we pick these number of blades, then these chords kind of go down almost by half. So 200 to about 100. This is a little bit over 50, and you know it's not exactly half, but it's pretty close. So the chord is scaling with the diameter. The solidity is helping with angle of attack as we get smaller, and then you've got these number of blades. And I thought this particular turbine might be interesting to look at, so I just chose a small one, 250 millimeters in diameter, and figured 7 blades and a chord of 21 millimeters. So I wanted to see what that looked like, and that's why I designed the turbine that I did. This is the base of the wind turbine. It goes on top of a 1-inch EMT tube. It just slides on with some kind of press fit features there. And this is a 2208 gimbal motor, and this is acting as the generator. And it mounts to the base with 4 M4 bolts, 8 millimeters long. You can see them in there. And the rotor mounts to this this gimbal motor, and there's with 3 M3 bolts, also 8 millimeters long. Okay, the arms are printed in 2 halves. And we'll glue those 2 halves together. Smooth it out. Looks pretty good. So I'll just put these 2 together. This green O-ring material helps line it up. And then you just kind of smear it back and forth. And just put this in so that it helps it line up too. This is going to be the pivot pin. It's important that that lines up so this can pivot well. And then just make sure good. And then just clamp it up so that it's good and tight. Added here. So here's the wing being printed. I print both halves together, and this is a little collar to kind of hold around where the counterweight mounts. And I got this little carbon fiber. It's 1.5 millimeters by 200 millimeters long. A little bit of epoxy in there too. It goes in this little slot. Okay. Get a little extra in there. Alright, so we put these 2 together, 2 halves. Lined up. And I've got this little collar here just to give this little holder some extra strength. There's the wing, and I'm just going to set it down, put a little weight on it, make sure it sets up. Okay, here's the counterweight. I haven't glued this in yet, so I could take it in and out, but anyhow I picked different lengths of screws and numbers of washers until this thing was approximately level, and I have some adjustment one way or the other. So this is an 1.25" number 6 screw. There's 2 nuts on there, 5 washers, and it's got some adjustment one way or the other, and it's approximately level, so I can tweak it. So anyway, that's how I came up with the counterweight. You'll notice that it's got a certain period of oscillation here, and we want that to be low enough so that it can react fast when it's spinning around. So whether that's fast enough, I'm not sure. It looks like it might be kind of close. We might be running close to this resonant frequency here, so we'll see what happens. This is the turbine assembly. It's got a hub that fits on top of the gimbal motor, and it has the holes for the mounting screws. Not much wind today, about 1.2 to 1.5 meters per second tops.